All right, so last time we saw the wave particle duality nature of an electron. Now we're going to take a little bit more look at it. So if you remember back to our experiment, basically we shot one electron at a time, and we said that this electron goes through both slits at the same time because it's a wave and then interferes with itself. And so you shoot one at a time, but then you add them all up and basically it behaves like a wave. And so scientists back in the day, they're like, this is nuts. This doesn't make any sense. It's not working. We're going to outsmart this electron. And what we're going to do is we're going to watch it. We're going to watch this electron. We're going to watch this electron go through one of these two sides. And so what we're going to have here to watch it is a laser, right? We're not small enough. We can't actually see an electron. And so we've got this laser to watch the electron. So every time the electron passes this laser, we're going to see a little blip, and it's going to tell us which one of these two slits is the electron coming through, right? Is it coming through this one, or is it coming through this one, or is it really coming through both? And so what scientists saw was sometimes they'd get a blip here, or sometimes they'd get a blip down here. They would never see it come through both slits at the same time. And then, they kind of let it go, shoot one electron at a time. And then what they saw was just these two stripes, right? It looks different than it did before. And in this case, the electron is actually behaving as a particle, right? So only see one or the other. And the electron is behaving like a particle. When it's being watched. So when you're not watching it, it's behaving like a wave. And when you are watching it, it's behaving like a particle. So that's a pretty nutty idea that an electron is doing something differently just because you're watching it. I mean, electron doesn't have a mind. It can't think. How does it know that you're watching it? So this is what's known as the measurement problem in quantum dynamics. And so let's take a look at that. And the issue comes from the fact that in order to measure something in our physical world, we have to interact with it. And when we interact with something, we actually change its value. So we interact with our world to observe or measure it. So let's take a look at a macro look. Let's say we got this hot block. It's really hot, right? Hot block. And so it's a really crappy thermometer, but it's a thermometer, right? A thermometer is an instrument we use to measure the temperature of something, right? So that's the initial state. If we let some time pass by, since this block is hot, the thermometer is going to tell you that it's hot. So the thermometer is going to go look at something on the left to something on the right here, right? The red's going to go up because it's hot, right? So the thermometer is going to read the temperature. But think about how it's reading this temperature. In order for this thermometer to read this temperature, what's happening is the heat is leaving the block and going into the thermometer, right? And while we're measuring it. So technically, since, right, so block lost heat to thermometer. Right, and so since technically the block lost some heat, the block should be colder. Right, anytime something loses heat, it goes down in temperature, and so this block lost heat, so it should be colder. So does that mean that our thermometer is not accurate? No, our thermometer is still accurate. So this is technically correct. Technically, yes, it does become colder, but we're just removing a tiny, tiny, tiny bit of heat that it doesn't change the result, right? So, but only removed an insignificant amount of heat. right? So we just removed a tiny amount. So our thermometer, our measurement isn't actually affecting our experiment. That's where the issue comes in when you're trying to study electrons, though. Electrons are super, super, super tiny, so you cannot interact with an electron without significantly changing its properties. So something like a hot block, we can measure it because we can interact with it without changing the system because we're just removing a tiny amount of its energy. When we try to do that with an electron, it's so tiny that we can't remove a tiny amount of electron. Any observation that we make on the electron is going to be significant enough to change its value. And so this is what this uncertainty principle means. It's that we have uncertainty in our measurements. So what we say here is that electrons are so small that we can't measure where it is. This is known as its position. Right? That's what we tried to do with this laser. We tried to measure where it is. So we can't do that without changing its momentum. And momentum is basically just velocity and direction. So on the right here, when we interact with this electron with this laser, we learn about its position, but we lose information but we change its momentum, and thus it ends up looking different. Whereas in this one, we don't know information about its position, and so we get more accurate information about its original momentum. But when you get to particles that are so small like electrons, you can't have a complete picture of this stuff. So where it is, that's dependent on its particle properties. Right? Think about a particle. You can tell where a particle is. If you think about a wave isn't really in one place or another. It's spread out through stuff. So that comes from its particle properties, and its momentum actually comes from its wave-like properties. If you think about velocity here, the velocity here is going to be equal to h mass times lambda, right? So it's actually dependent on the wavelength. So it gets its position properties from its particle nature, and it gets its momentum or velocity from its wave-like nature. And we actually can't know both at the same time. So we'll explore that a little bit more in this next section.